Welcome everyone. Today we'll embark on a journey into the world of apportionment, a fascinating concept that lies at the heart of fair decision making. Apportionment is the process of allocating resources or representations among groups, ensuring everyone gets a proportionate share. It plays a crucial role in various settings, from distributing seats in a council to allocating government funding.
But achieving fairness can be tricky. Imagine a scenario where you have 10 seats on a council and need to divide them fairly among 4 cities with different populations. How do you ensure that each city is adequately represented without giving undue advantage to larger populations?
This is where the power of mathematics comes into play. We'll explore two prominent apportion methods, Hamilton's and Jefferson's, uncovering their unique approaches to achieving a balanced outcome.
Moving on, let us explore the Hamilton's method, which is mainly all about upholding population standards. We start by calculating a standard population for each seat by dividing the total population by the number of seats. Alexander Hamilton introduced the method now known by his name, which gained approval from Congress in 1791, but faced a veto from President Washington. Although initially rejected, it was later adopted in 1852 and utilized until 1911. Hamilton's approach involves determining with precision to several decimal places the allocation for each group. Given his focus on the matter of congressional representation, we will employ the terminology of states and representatives. Hamilton addresses the questioning of determining the appropriate number of representatives each state should have.
These are the steps to the Hamilton method. Number 1, begin by establishing the number of individuals each representative should represent. Achieve this by dividing the total population of all states by the overall number of representatives. This outcome is referred to as the divisor. Number 2, proceed to divide the population of each state by the divisor to ascertain the number of representatives it should be allocated. Keep a record of this result with several decimal places, known as the quota. Since only whole representatives can be assigned, Hamilton addresses this by taking the following steps to resolve the whole number predicament. Number 3, disregard all decimal portions of the quotas while retaining the decimal values. These are now known as the lower quotas. Sum up the remaining whole numbers, always ensuring that the result is less than or equal to the number of representatives. The or equal to condition is rare and specific circumstances may apply. Number 4, assuming the total from step 3 is less than the overall number of representatives, distribute the remaining representatives one by one to the state with the largest decimal parts of the quota until the desired total is achieved.
For further understanding, here is an example. Delaware consists of 3 counties: Kent, Newcastle, and Sussex. The state's House of Representatives comprises 41 members. If Delaware opts to distribute the representation based on county lines, even if it's not mandatory, let's assume for the scenario, we'll apply Hamilton's method for apportionment. The county populations sourced from the 2010 census are as follows.
Number 1, determine the divisor. The first step involves determining the divisor. We achieve this by dividing the total population of all states by the overall number of representatives. Total population equals 897,934 divided by overall number of representatives equals 41, resulting in 21,900.82927.
Now, we determine each county's quota by dividing the county's population by the divisor. Here are the following computations. 162,310 divided by 21,900.82927 is equivalent to 7.4111. 538,479 divided by 21,900.82927 is equal to 24.587. And 197,145 divided by 21,900.82927 is equal to 9.0017. With that, the quota of each county is as follows.
3 lower quotas. Now we remove the decimal parts of the quotas. From the table, the decimal places from the quotas are removed, leaving a whole number which should be summed up. 7 plus 24 plus 9 equals 40. Always ensure that the result of the sum is less than or equal to the total number of representatives. In this case, we have a result of 40 less than the total of 41.
4. Assigning the representatives. For the last step, we distribute the remaining representatives one by one to the states with the largest decimal parts of the quota until the desired total is achieved. Since we need 41 representatives, and this only gives 40, the remaining one goes to the county with the largest decimal part, which is Newcastle. Thus, the final allocation are as follows: Kent with 7, Newcastle with 24 plus 1, making it 25, and Sussex with 9. Understanding Jefferson's method. Next, let us delve into understanding Jefferson's method, which is a method that takes a different path. Instead of quotas, it focuses on ensuring basic representation for all cities. After Washington vetoed Hamilton's method, Jefferson's method was adopted and used in Congress from 1791 through 1842. Jefferson's method initially aligns with Hamilton's, involving the same steps of determining a divisor, calculating quotas, and removing decimal parts. The key difference arises in Jefferson's approach to resolving the resulting shortfall in the total number of representatives. Rather than directly adjusting quotas, he contends that the problem lies in an oversized divisor. Jefferson iteratively revises the divisor, computes new quotas, eliminates decimal parts, and evaluates the total until finding a divisor that achieves the required total.
With that, here are the following steps. Number 1, determine how many people each representative should represent. Do this by dividing the total population of all the states by the total number of representatives. This answer is called the standard divisor. Number 2, divide each state's population by the divisor to determine how many representatives it should have. Record this answer to several decimal places. This answer is called the quota. Number 3, cut off all the decimal parts of all the quotas, but don't forget what the decimals were. These are the lower quotas. Add up the remaining whole numbers. These answers will always be less than or equal to the total number of representatives. Number 4, if the total from step 3 was less than the total number of representatives, reduce the divisor and recalculate the quota and allocation. Continue doing this until the total in step 3 is equal to the total number of representatives. The divisor we end up using is called the modified divisor or adjusted divisor, shorten and rephrase.
Example. Let's continue on with the same example from the Hamilton method. Delaware consists of 3 counties: Kent, Newcastle, and Sussex. The state's House of Representatives comprises of 41 members. The county populations, sourced from the 2010 census, are as follows. Solution. From the previous computation using the Hamilton method, we found the quotas with the original divisor, 21,900.82927. To start off the solution, we originally have 41 representatives, and the Hamilton method divisor gives only 40. Thus, we must reduce the divisor until we get 41 representatives.
Solution. With that, instead of 21,900.82927, let's try the divisor 21,500. 162,310 divided by 21,500 equals 7.5493. 538,479 divided by 21,500 equals 25.0455. 197,145 divided by 21,500 equals 9.1695. This gives us the required 41 representatives. If we had fewer than 41, we'd need to reduce the divisor more. If we had more than 41, we'd need to choose a divisor less than the original but greater than the second choice. With that, we get the final representation of 7, 25, and 9 representatives, giving a total of 41. Thus, us that the Jefferson's method avoids the problems of an apportionment resulting in a surplus or a deficit of house seats by using a divisor that will result in the correct number of seats being apportioned.
Overall, both Hamilton's and Jefferson's method achieve fair representation, but they take different approaches. Hamilton's method adheres strictly to population standards, giving larger cities more seats. Jefferson's method, on the other hand, ensures minimum representation for smaller cities while still acknowledging population differences.
The choice between Hamilton's and Jefferson's method boils down to priorities and context.
The most suitable method depends on the specific context and priorities. If strict adherence to population standards is paramount, Hamilton's method might be preferred. However, if ensuring basic representation for all groups regardless of size is crucial, Jefferson's method might be the better choice.
Ultimately, understanding the principles behind both methods empowers us to make informed decisions regarding resource allocation and representation. Whether it's deciding the number of representatives in a legislative body or distributing funding among different regions, the principles of apportionment guide us towards fair and equitable outcomes.
To further enhance our understanding, let's delve deeper into some real-life examples of apportionment in action. Imagine having to allocate seats on a school board among different districts with varying student populations. Or consider distributing federal grants to different states based on their population and economic needs.
Applying our knowledge of Hamilton's and Jefferson's methods to these scenarios, we can analyze their advantages and limitations, leading to well-informed decisions that benefit all stakeholders.
As we conclude our exploration of apportionment, we leave you with a thought-provoking question. How can we leverage the power of mathematics to ensure fairness and equity in the allocation of resources and representation?
By understanding the principles of apportionment and engaging in critical discussion, we can strive towards a future where everyone has a voice and is adequately represented.
Thank you for joining us on this journey into the fascinating world of apportionment. We hope this video has equipped you with the knowledge and tools to engage in constructive dialogue and contribute to building a fairer and more equitable society.